Okay, we're about to do part 2 of H3O, vector velocity, speed, unit vector, and relative position. We're going to talk about relative position now. So, relative position. If A is in a position somewhere here, and B is in a position over here, using these vectors, relative position of B from A. So if I want to go to B from A, position of B from point A. So I'm going from point A to point B. I'm going to be able to do the relative position vector of B minus the relative position of A. So this is useful when you're trying to find an object of a particle relative to the other position, not necessarily to the origin. Okay, and also for finding the distance between the objects given a particular time. Okay, so we're going to experience that with example 14. Okay, so example 14. Here we go. At time 0, we've got a boat that is at this position. Okay, so here's my initial position, and this is boat A, right? And it's traveling at this speed and this direction. Okay, so the x component of the displacement east from the origin, and the y component is due north. Okay, all the distances are in meter. So find an expression for the position of the vector in terms of time. Okay, so remember, we're going to do what we just did on the previous example, that the velocity equals the speed times the unit vector. Okay, I don't want to put parentheses. Okay, so we know that it's in this direction. We know that B equals 3, -4. Right? So we're trying to find the unit vector. We've got our speed. So we need to figure out magnitude of B. So the magnitude of B, we just did this a second ago, which is square root of 3 squared plus -4 squared. And you should already know that that's 5 meters. We just did this a few seconds ago. So my unit vector, or is equal to speed times direction vector divided by the magnitude. Right, because direction vector divided by the magnitude, that gets me my unit vector. My speed times my unit vector is going to give me my velocity. So what we have here is we've got 4 times 1/5, and then times my direction vector, which is 3, 4. And that simplifies to, so 4 divided by 5 times 3. 4 divided by 5 times 3, that's going to give me 2.4. Oops. And then the y component is 4 divided by 5 times 4, and I get 3.2, negative 3.2. Right? Okay, so that should have been negative there. Okay, so now I can rewrite this in the form of, because this is my, what did they call it? the relative position of A can be written as the initial position RO plus my velocity T. And so we're writing an expression for the position vector of A at time t. So this is going to simplify to my relative position A is going to be equal to 2, 5, because that's when we're starting, plus my position vector, my velocity, 2.4 and negative 3.2 t. So I've got my velocity, we just calculated, was this. Okay, my initial position was 2.5, so we got this. So now we've got my expression for the position vector RA at time t. Okay. Boat B has a position vector here. Oh, that was nice of them to give us this. Okay, show that the two boats do not collide. So to show this, we need to first equate the x components. Okay, so the x components is going to be 2 plus 2.4 t equals, and then the x components here are 3 plus 2 t. Okay, so I could subtract 2 on both sides here, and I could subtract 2t on both sides here, and then I get 2.4t minus 2t gives me 0.4t. 3 minus 2 is going to give me 1. And if I do t divided by 0.4, I get t equals 2.5. Okay, so now, when at time 2.5, my x values are the same. So now we want to see if the y values are the same at t equals 2.5. And if they are the same, then they collide. If the y values are not the same at t equals 2.5, then they don't collide. Because at 2.5, the x values are the same. We want to see, are the y values also the same at t equals 2.5. So with here we've got 5 minus 3.2 t equals what does that equal? We're gonna well, I guess that's ya, right? So let's plug in 2.5. So we have 5 minus 3.2 times 2.5 for ya, and then we get simplify this, and we get ya equals negative 3. Now for yb, we've got negative 2 plus t. I'm going to plug in negative 2.5 in place of t. Yb equals negative 2 plus 2.5. Replace t with 2.5. And then I end up with yb equals 0.5. So since these are not the same, since the y components are different, since the y components are different, when the x components are the same, They do not collide. Okay? So now we're going to have to use the calculator here. And there's calculator instructions on your handout, and it looks like this. But we're going to do this together, so don't you worry. Okay. So find the shortest distance between the two boats. Okay, so the shortest distance, well, okay, first of all, the distance between the 2 points is going to be RB minus RA. Okay, so the distance between the boats is this, right? So RB minus RA. If we're just trying to find the distance, it doesn't matter which one's first because we're going to do absolute value to find the distance anyways. So RB is, here we go, 3 plus 2t, negative 2 plus t, that's RB, right? 3 plus 2t, negative 2 plus t, minus RA, which is 2 plus 2.4t, and 5 plus negative 3.2t. Okay, so now we're going to combine the like terms, and we end up with 1 minus 0.4t and negative 7 plus 4.2t. Okay, so now we need to find the magnitude of this. So to figure out the magnitude of RA, or RB minus RA, we're going to find the magnitude of this. So 1 minus 0.4t and negative 7 plus 4.2t. So to figure out the magnitude of that, I'm going to type in 1 minus 0.4t squared plus negative 7 plus 4.2t quantity squared. Okay, so let's do that right now. So okay, on y equals, okay, square root, parentheses, 1 minus 0.4 x, close parentheses, squared, plus, open parentheses, negative 7 plus 4.2 x, close parentheses, squared. Okay, so I've typed in my equation here, and now I can graph it. So I'm going to do zoom 6 to get a standard graph. And so I've typed this in here, and then my graph looks like this. So the shortest distance, so we're going to type this y equals this, right? And then you're going to hit y equals that. And then so now the shortest distance is when we find the minimum. Okay, so so I'm going to press second trace to graph, and we want to find the minimum. So I'm going to hit 3, enter. Oh, let's try that again. Second trace. I'm going to down 3 for minimum, and then it says left bound. So I need to go to the left side. Enter. That says right bound. I'm going to go to the right side. Enter. Guess, I hit enter, and now it tells me the minimum is this coordinate. So the minimum, this coordinate, is 1.67, comma 0.332, and so I'll just rewrite it. Okay. So what did we do? We pressed graph, then second trace minimum, right? And then we did left bound, right bound, guess, enter, and we got this coordinate. So the minimum distance is the y value, this distance here, which is 0.332 meters. And this happens when the x distance is our time, so when time equals 1.67 seconds. Okay. Last question. We don't need a calculator for that, or at least we don't need. So what is the value of t when b is due east of a? So when b is due east of a, we set the y component equal to 0. Okay, so the y component is -7 plus 4.2 t. We're setting that equal to 0, and we get 4.2 t equals 7. Divide by 4.2, and I get t equals 1.67 seconds. Okay. So, what could we say about this? Okay. So, how do we find the relative position of A from point B? So we've got the two relative position vectors, and the relative position is when we subtract them together. Okay, how might we find the least distance from the two objects? So to find the least distance between the two objects, we find the magnitude of our relative position, and then we can use our graphing calculator to calculate the magnitude of the function. And the minimum distance, we said, was the y value. So maybe we should write that down. The minimum distance is the y value. I'm going to highlight that. Okay. And then how might you find the time when the bearing of one object to another is at the given direction? And we use the x value when at the minimum distance. X value at the minimum distance. Okay, so exercise 3O, H3O, not H2O. Ah! Okay, so you might want to check your answers. What have I done here? So we've got our initial position. Okay. The position vector A. And find the velocity. What did we do to find the velocity? Oh, okay. So B is another point later, right? So, and they told you after time is 2. So if the time is 2, I'm plugging in 2 in for the time. My initial position is this, B is this. Now we can calculate the velocity. So I could subtract 4 equals 2 plus 2x, and then to find the x value, subtract 2 on both sides, divide both sides by 2. My velocity x component is 1. Then I take 5 equals 1 plus 2v. 5 equals 1 plus the y value times 2. Subtract 1 on both sides, divide both sides by 2. I get my y value of the velocity. So I've got my y value of the velocity, which I'm using the 1 and the 2. Okay, so so part I, I've just found the velocity. Part II, we're going to find the magnitude of my velocity. So if the magnitude of my velocity, I use the distance formula, and there's my magnitude. All 4 of these are kind of the same process. Let me just go through C. Okay, so my initial position is 3, 1, negative k. My B location, the resulting location, is 1, 5, 1. So the time is 2, so I've plugged in 2 here, and we're trying to find the velocity vector. Okay, so I find the x, y, and z values of my velocity vector. So looking at the x values, I got 1 equals 3 plus 2x, and then I could subtract 3 on both sides, and then I get negative 2 equals 2x, divide both sides by 2. Let's look at the y values. I got 5 equals 1 plus 2y. Subtract 1 on both sides, I get 4 equals 2y. Divide both sides by 2, I get this. Now let's look at the z values. 1 equals negative 1 plus 2z. Okay, add 1 on both sides, I get 2 equals 2z. Divide both sides by 2, I get z equals z equals 1. So I use the negative 1, the 2, and the 1 for my velocity. Okay. Now to find the speed, I take the magnitude of that. Okay. These two are done the same process. Okay, I guess I've been highlighting speed orange, so let's just continue that same thing. We've been highlighting the speed orange, and we've been highlighting the velocity red. Okay. I'm just going to put this here and let you check your answers. Okay, I'm going to move it up. Okay. And the rest will finish in class.